You know, what happens when a perfect piece of code, something designed in the clean, quiet, theoretical world of a computer, actually meets the messy, unpredictable reality of a physical machine? Well, today we're going to explore that exact question, but with a twist. Our machine is a quantum computer.
See, this gap, the space between the flawless blueprint and the physical result, that's right at the heart of the entire quantum computing challenge. It's a story that shows us not just the incredible promise of this tech, but also its biggest hurdles. So, let's start with the blueprint.
So, every story needs a hero, right? For this one, we're going to start in a perfect, simulated world. It's totally free from any real-world interference. And here, we can design a completely flawless quantum program and see exactly how it's supposed to behave.
The program we're building creates what's known as a Bell state. Now, this is one of the simplest but most fundamental building blocks in all of quantum computing. It's a really simple two-step process. First, we hit a qubit with something called an H-gate. That puts it into superposition, that wild quantum state of being both a 0 and a 1 at the exact same time. Then a C-naught gate links it to a second qubit, and this entangles them. That creates that famous spooky action at a distance, a deep connection where measuring one qubit instantly, and I mean instantly, affects the other no matter how far apart they are.
Okay, so when we run this program in our perfect little simulation and measure the results, what do we get? We get a perfectly predictable outcome, a super clean 50-50 split. Half the time the qubits are in the 0-0 state, and the other half they're in the 0-1 state. That's it. No other possibilities. This is our baseline. This is theoretical perfection. So burn this chart into your brain.
But here's the thing. A program that only runs in a simulation is, well, it's just a thought experiment, right? The real test, the real moment of truth, comes when we take this perfect code and run it on actual physical hardware. This is where our little program leaves the safety of the lab and has to face the chaos of the real world.
And this brings us to the main event, the core conflict. In one corner, you've got the simulator. It's predictable, it's sterile, it's noise-free. And in the other corner, you have the real quantum hardware, a physical device that is vulnerable to every tiny disturbance from its environment. This is where we meet the villains of our story: noise, decoherence, and gate errors. And trust me, this is where things get really interesting.
Let's focus on the main antagonist here, quantum noise. The best analogy I can give you is trying to whisper a secret in a really loud, crowded room. Our qubits exist in this incredibly fragile, delicate state. So even the tiniest fluctuations, like a stray magnetic field or a tiny change in temperature, can be enough to mess up that state and introduce errors into our calculation.
So how do we bridge this gap? How do we actually send our program from its safe, simulated home into this chaotic, physical environment? Well, we need a gateway. And unbelievably, that gateway is now accessible to almost anyone through the cloud.
And that gateway is the IBM Quantum Platform. It's this incredible service that lets researchers, students, and enthusiasts from literally anywhere in the world write code and then run it on actual quantum processors. This is the bridge we're going to use to send our program into the quantum realm.
All right, the stage is set. We have our perfected Bell state program. We know all the challenges it's going to face, the noise, the decoherence. We've got our cloud portal ready to go. It is time to run the experiment on real hardware.
And just like that, with a few lines of code, we send our Bell state circuit off, not to a simulator, but to a real backend, a physical machine with a name, IBM Q Lima. Our program is now officially in a queue, just waiting for its turn to run on actual quantum hardware.
After a short wait, the results are back. So now we get to see what really happens. What happens when our perfect theoretical program smacks into the messy, noisy reality of a physical quantum computer? Let's compare the results.
First, just a quick reminder of our ideal world. The simulation gave us that perfect 50-50 split between 0-0 and 0-1. That was the expectation, the dream.
And this is reality. Now, at first glance, you might think, hey, that looks pretty close. And you're right, the 0-0 and 0-1 states are still the overwhelming majority. But look closer. See those other two little bars? The 10 and 11 states? Those should be impossible. They should not be there at all for this circuit. That small bar, that little 5%, that is the fingerprint of quantum noise.
So, why? Why is there a difference? This question right here is maybe the most important question in quantum computing today. What does this gap between theory and reality actually mean for the future?
And this leads us to our final and honestly our most important point. Because this imperfection that we're seeing, it isn't just a simple bug. It is the single biggest challenge and the most important area of research in quantum computing today.
So let's name these culprits. Let's look at the rogues gallery. Those little error bars are the result of everything we talked about. That environmental noise, decoherence, which is just a fancy way of saying the qubits are losing their quantum magic, and tiny imperfections in the physical gates that operate on them. It's not any single one of them to blame, it's the combined effect of a noisy, imperfect world.
And this is the key takeaway. Seeing these errors, it is not a failure. It actually defines the era of quantum computing we are in right now. It's called the Noisy Intermediate Scale Quantum Era, or NISQ for short. Learning to manage this noise, to mitigate it, to even work around it, that is the central challenge that thousands of scientists are working on. This is the frontier.
And what this really shows us is the path forward. It's not just about building better, bigger, more powerful hardware. It's about designing smarter software that is aware of the noise. And this leaves us with the defining question for the entire field, for the next decade. How do we code for a world that by its very nature just isn't perfect?